is brought to you by leXsolar, understanding new energies with teaching systems and training systems for school, technical training and further training, and the YouTube channel Innovative Technology and Energy Transition. The term smart grid covers a wide range of technical solutions in the energy system. The term actually refers not only to the grid, which is responsible for transmission and distribution, but also to the integration of generators, consumers, and storage systems. The grid should become smarter through the additional use of measurement, control, and communication technology. In this video, we will first take a look at just how smart our current power grid is and where more intelligence is already firmly planned and implemented. Then I'll show you a simple example of where more intelligence will be needed in the future and what that intelligence might look like. To look at the current state, you need to understand how our grid came to be. In the past, there were a few larger power plants that always delivered exactly the energy that consumers needed. The large power plants were connected directly to the transmission grid, the upper levels of the grid, which were monitored and controlled by control rooms. The lower distribution grid levels were simply dimensioned large enough to be able to supply consumers reliably on a permanent basis. As a result, there is very little measurement technology and control options at these levels. Due to the energy transition, generation is becoming more decentralized through PV, wind, and CHP plants, and the number of large power plants is decreasing. As a result, the distribution grids will be more burdened. Therefore, they must either be significantly expanded, which is very expensive, or become smarter. The first major step in this process, which is already in progress, is the smart meter rollout. A smart meter is an intelligent electricity meter. It is smarter in that it has a direct communication interface and can transmit measured values directly. In addition, in the future, a smart meter could also record not only the electricity consumed, but also other grid state variables such as voltage. In practice, these smart meters are now first being installed at large consumers, and the smart meter rollout has been stopped for the time being by the Kurds in 2021. But let's take a look at a simple example of why more intelligence is needed in the distribution grid as a result of the energy transition. The figures and calculations are greatly simplified here, but they clearly illustrate the potential problems that can occur in the distribution grid. Let's consider a street in the distribution grid with 5 single-family houses. Each house has a 10 kilowatt PV system with storage, and the families drive an electric car that is charged by a wallbox with 11 kilowatt. The lines in the grid are assumed to be resistive in a simplified way, resulting in a voltage drop on the line according to U equals R times I, which is proportional to the current. The voltage at the transformer at the beginning of the road is assumed to be fixed, simplified single phase with 230 volts. According to the standard, in order not to damage the connected devices, the voltage may only deviate by plus minus 10%. Which means between 207 and 253 volts. In the first summer scenario, we consider a sunny day. All PV systems feed in at full load since the household storage is already full and consumption is low since no one is at home. Approximately each household feeds in a current of 10 kilowatt divided by 230 volts, rounded down to about 40 amps. The total current in the foremost section is thus 5 times 40 equals 200 amps. If we assume a line resistance of 0.04 ohm, the voltage at the first house is 238 volts. At the second house, the voltage is 244.4 volts. If we continue to calculate in this way, the voltage at the last house on the street is 245 volts, which is already just above the limit of the voltage band. In the second scenario, it is winter and there has been very little sunshine for days, so the storages are empty. In the evening, the families come home and all charge their electric car at full load, start cooking and thus arrive at a total consumption between 11 and 13 kilowatt, which corresponds to a current of 60 amps per house. Calculating the voltage again, we get 218 volts at the first house. At the end of the street at the fifth house, the resulting voltage is 194 volts, which is well below the 207 volt minimum. Even if this example is clearly simplified and exaggerated in the simultaneity, it still shows the problem. Whereas the past there was no feed-in in the grid and thus the voltage at the transformer could be somewhat higher than 230 volts, the voltage band in the distribution grid is now being exploited in both directions and the outputs are increasing significantly in some cases due to electric cars, heat pumps and PV. Below we'll look at 3 different smart solutions for the simplified example. The least smart solution would be to rip out the road, lay more copper, which means a thicker wire which has a lower resistance. The voltage drops will be lower that way. However, the cost of doing that in all distribution grids across the country would be enormous. A smarter solution would be to replace the transformer with the on-load tap changer, a transformer that can adjust the transmission ratio and thus the output voltage. Based on a measurement of the voltage at the end of the street at house 5 or the power transformer, the output voltage of the transformer could be controlled this way. So in the summer scenario, the voltage at the transformer could be reduced, and in the winter scenario, the voltage could be increased, so that in both scenarios, all voltages are within the voltage band. Even smarter solutions from research are often in the direction of increasing the intelligence of the energy system in each household by having all homes have measurements and allowing the system to communicate with each other or a central location. For example, battery storage could be deployed so that all PV systems never feed full power into the grid. The charging powers of the electric cars could be reduced if necessary, or for extreme cases in winter, the home storage systems could be charged beforehand. Artificial intelligence and variable electricity prices models are also often used in this process. This makes slower or later charging of the electric vehicle, which is not needed again until the next day anyway, cheaper and thus preferred by the families, and grid expansion can thus be avoided in very many places. You can find more interesting videos like this here on the YouTube channel Innovative Technology and Energy Transition. You want to understand new energies or teach them to others with teaching systems and training systems for school, technical training and further training? Then check out the leXsolar homepage now.